Hi. What we've been doing, we examined the combination circuit synthesis by using the Kuhn-McCluskey method. Now we are going to introduce a new method, which is Karnaugh map method. We examined what Karnaugh map is, how to represent a function by using a Karnaugh map. We have done that, and we have learned two terminology. One of them related with subcube, and the other one the neighbor cells. So order is changes. Then we learned what neighbor cells is, and then we learned subcubes. Subcubes represent variable elimination operation. We have examined all that. Now we are going to apply the Karnaugh map method now. Either we use the Karnaugh map method or we use the Kuhn-McCluskey method. Our aim is to find the minimal function. So why we are giving two different methods, we are going to explain it in this comparison of the two methods. So this video is related with this Karnaugh map here. Escape. Let me check whether this is on or off. Okay. Let's go in now, present. So our examination, we might end up with saying that if we find a high order alt cube, subcube, high order subcube means you applied the variable elimination operation many times. High cube, high order subcube. So higher the order of the subcube means corresponding product term has got less variables in it. Less variables in a product term is a potential for a prime implicant. We know that in minimal functions we've got prime implicants. So you might say that higher order, if you find a higher order subcubes, then we end up with minimal function. At the beginning we might consider this, but there is a counter example to this one. Look at this function now. Has got 2, 4, 8 ones in it, this function. And there is a subcube here, second order subcube. This is a bold line here. Tells me this, you see that one here, as the second order subcube corresponding product term. For the other ones, there is a subcube here that is, this one was second order, but this one is first order. Since it is first order, one variable is going to disappear. So the corresponding product term has got 3 variables in it. This one is another first order subcube, corresponding product term is this one. And this one, another first order subcube. This is the product term. This is the last first order subcube, corresponding product term is this. Now if you consider now, choose the highest order subcube first. So if you choose this one, you have chosen this, isn't it? But if you change the order, if you choose the 3 variable included product terms corresponding first order subcubes, I mean this subcube, this subcube, this subcube, and this subcube. So this subcubes tells us when you choose these subcubes and put it in the minimal function, you cover all the ones in the function, isn't it? because all 8 ones are included in these first order subcubes. So you do not need to add any other product term to this, because a new product term you add is not, it is going to be trivial, isn't it? Because you already have got all the ones in it. Why do I have to choose these first order subcube? The answer is these subcubes are essential prime implicants. Let's check it. Because of this one here, not this, but this one here, this first order subcube is an essential prime implicant. Why is that? Because this one is included only in this subcube, and there is no any other subcube which includes this one in it. Therefore, it is an essential prime implicant. So this is essential prime implicant. Because of this one, this is another essential prime implicant. Because of this one, this is another essential prime implicant. And because of this one, this is another essential prime implicant. We already know that minimal functions must have all the essential prime implicants in them. So we have to choose all these prime implicants, essential prime implicants, sorry. So when we choose all these 4 first order subcube essential prime implicants, we cover all the ones in the function. So we do not need to add any more product term to this, because this is going to be trivial. Therefore, this second order subcube is a trivial product term and shouldn't be added to the minimal function. So conclusion is quite interesting here. In the Kuhn-McCluskey method, we first find the prime implicants, and then we find the essential prime implicants in the prime implicants table. You see one column has got one mark in it, as lead us to find the essential prime implicant. So we find the prime implicant first and then essential prime implicant. In the Karnaugh method, first we've got to find the essential prime implicants and then choose the additional minimum number of prime implicants to those essential prime implicants. Okay, that is the main difference. So we can do some more examples. Let's do it in open board now. Let's escape from here. Leave it down. Put that in. So we've got to transfer it open board. Have I opened the open board? Let me, okay, open board. Okay, here we are. So there is a Karnaugh map here. This Karnaugh map represents this function here. These two functions are not different. I should have corrected it. It's the same function, isn't it? Why it is the same function? Because you see we've got true min terms. This shows us the max terms, isn't it? This tells us where this function has got 0 values. Here, this shows us where this function has got 1 values. So I put in the Karnaugh map the 1 values only. The other 6 0 values are those. So if you consider zeros, that means you're considering second canonical form related minimal function. If you are considering 1, so you're considering first canonical expansion minimal function. So same function. Here you are. So this is G representation, Karnaugh map representation of G. This is Karnaugh map representation of this G showing 1 in it. Ones in it. Now, okay, so we said the rule is known. The rule is we're going to find the essential prime implicants first. How we're going to find that? Just start now. When you say that a 1 covered by one prime implicant but not any other prime implicants, So there is a separate one. That means around this one there aren't so many ones, because so many ones means there could be more than one prime implicants covers this one. Look at this one here. This seems a bit separate. Why is this separate? Because this side is empty, this side is empty. There are two sides, two neighbors that are not empty. So there is a second order subcube which covers this one in it. That is this one, isn't it? Now I am considering now whether this second order subcube corresponds to essential prime implicant or not. So our claim is, my claim is, due to this one, this is an essential prime implicant. Why is that? I am looking around here. Is there any other prime implicant which cover this one in it? For example, when I said any other prime implicant apart from this one, which includes this one in it. So this has got, there is a second order subcube here, does not cover this one. There is another subcube here, do not cover this one. There is another subcube here, second order, does not cover this one. And there is no any other first order subcube which covers this one in it as well, apart from this second order subcube. Because within this second order subcube there is first order subcube here, but this is inside this subcube, isn't it? So we are saying another subcube which covers this one. So I couldn't find. So therefore, because of this one, not for this one, not for this one, not for this one, because of this one, due to this one, this is a subcube. Why not for this one? Because for this one there is a subcube here, there is another subcube here. If there is a one which covered by more than one prime implicants, then this doesn't lead us to an essential prime implicant. But this one does lead us to an essential prime implicant. So this is an essential prime implicant. The corresponding prime implicant to this one is X, a product term corresponding to this second order subcube is X2, X3 prime. How I wrote that? So in here, since it is second order, two variables is going to disappear. These variables are going to be the ones of which values are changing. X1 variable value, 0 here, 1 here, is changing for this subcube. Which not changing is the second one, that means second variable. X2 is not changing, so I put that X2 here. Since the value is 1, X2 itself has been written in the product term. What about X3 and 4? So for this subcube, X3 variable is not changing and the value is 0, then X3 prime came in. X4 value is changing, it disappeared. So second order subcube, two variables gone. These are X1 and X4, and the other two variables which are not changing are going to seen in the product term. Okay, so now change the color, make it this one, maybe the black one. So look at this one. This one is another a separate one as I see it. Why is separate? This side is empty, this side is empty. And there is a subcube, second order subcube, which covers this one in it. This is that one. Okay. Now, question. Is there any other subcube or any other prime implicant which cover this one in it? There is no one. The red one here does not cover it. These four ones do not cover this one either. So therefore, this is an essential prime implicant. This essential prime implicant is x1 and x2. Why is that? If you consider this column here, for this column, x3 and x4 variables values are changing, isn't it? x1 and x2 variable values is not changing, so x1 and x2. So let's come to the last one. This is a separate one once again to me, but not this one, but this one. This covers, this one is included in that subgroup. And there is no any other subgroup which covers this one in it. I cannot say this for this one, for example. For this one, there is a subgroup of this green one. Also, there is a subgroup this one, isn't it? So there are two subgroups which includes that one in it. So this one do not lead me to a essential prime implicant. But this, yes, it leads me to a essential prime implicant. So what is the corresponding essential prime implicance for this one? X, for those four ones, x1 value is changing, x2 value is changing, and its value is 0, so x2 prime. For those four again, if I compare these rows, x3 value is changing, disappears, x4 value is 0, not changing, x4 prime. So minimal function for this function is x1 and x2, x2, x3 prime, and x2 for x4 prime. What does this mean? You got 1, 2, 3 AND gates. Each of them has got Fenin 2. Add them up with an OR gate. So this is the G mean, minimal G function. So this is first type canonical form minimal function. So it is AND/OR type. So if you consider the original function here has got 10, 2, 4, 6, 8, 10. So it has got 10 ones in it. 10 ones mean 10 AND gates and one OR gate. Fenin is 10, isn't it? Instead of this, you've got this. So much better than the non-minimal first canonical expansion realization of the function. Okay. Now consider now the same function and consider the max terms. So we're going to consider the second, maybe this one, second canonical form, canonical for minimal function. So it's going to be OR/AND type. So it's going to be which type? Product of sums. Product of sums. This one, sum of products. Sum of products. Maybe I should written here sum of products and/or product of sum or AND. So the method is the same again. We are going to look for 0 included subcubes, and I am going to look for the essential prime implicants related with these zeros. So look at this one now. For this 0, I can easily say that this is a second order subcube, and this 0 does not cover it by any other prime implicant. It's not covered by any other subcube. So Can I say it for this 0? I cannot say it because this 0 is included in this second order subcube. Also it is included with this first order subcube. So for this 0, I cannot say this is a essential prime implicant. But because of that, this 0 that I marked with the dot of red dot here, it is a second order subcube which corresponds to essential prime implicant. So what is the value of this essential prime implicant? So x1 is changing value, x2 is not changing, x2 prime, not the prime. I especially then done that mistake. Not the prime because this is the second canonical form. So we are considering this 0, we are going to find the opposite, isn't it? So for these zeros now, x2 value is not changing, x1 value is changing, x1 value disappeared. x2 value is 0, then I'm going to write x2 without prime. This is going to be a sum term corresponding to this one, sum of products form, a product of sums form. So we're going to find the sums and then product them. So x2. If you compare those two rows now, which covers this second order subcube, x3 value x3 variable value is changing, but x4 value is not changing. So x3 is going to disappear, x4 is going to stay in. Since the x4 value is 1, it's going to be plus x4 prime, the opposite of this case. So I found this is a essential prime implicant. This corresponds to essential prime implicant. This is a second order subcube. Two variables disappears. So if you consider now this 0 here, not this one, but this one, this first order subcube is an essential prime implicant. It corresponds to essential prime implicant. Why is that? Because there is no any other subcube which covers this 0 in it. That means there is no any prime implicant which covers this 0 in it. By definition of essential prime implicants, this is an essential prime implicant. So what is this essential prime implicant as a sum term? So x1 and x2 value is not changing. For x1 it is going to be itself. For x2 it's going to be x2 prime. So for those two, x4 value is changing, so x4 is going to disappear, x3 is not changing, the value is 1, so prime of this is going to come in, x3 prime. So G minimum function for the second canonical form minimal is equal to this x2, x4 prime, x1, x2 prime, x3 prime. So if I draw the circuit now, it's going to be one OR gate, another OR gate, this x2, x4 prime, and that has got 3 inputs, x1, x2 prime, x3 prime, and output of these OR gates are multiplied. This is that thing. This is G min. So if you compare those two, what you say you've got 3 gates here and you've got 4 gates here. This is better than this one. Okay. We should say that we cannot say that if the number of zeros is less in a function, then you've got to consider the second canonical form minimal function. So this could be proved by giving a counterexample, but I am not going to give it here. Therefore, since we cannot say which minimal function finding is better than the other by looking at the number of zeros or ones in a function, then we've got to find two minimal function for two different forms, for two different canonical forms, and then compare the result by comparing this circuit. Okay, which one is better? We are going to choose that one. That is the engineering practice. You're not going to find all the one type of canonical form minimal function. You're going to find both canonical form minimal functions and then make the decision which one is better or not. So come back now again to our Prezi. Okay. We have done this, let's say. There is this, we have done this. So we have done a Karnaugh map example for 4 variable functions. What about 5 variable functions? When it is 5 variable functions, so Karnaugh map becomes bigger. When it becomes bigger, how become bigger? This is a Karnaugh map, 4 variable Karnaugh map. This is another 4 variable Karnaugh map. What is the difference is this, you see, this side, x1 value is equal to 0. For this Karnaugh map, x1 value is 1. So this order here in this Karnaugh map columns and this Karnaugh map column is symmetrical according to this axis, isn't it? For example, 1 0 1 0, 1 1 1 1, 0 1 0 1, 0 0 0 0. So this order, if you read the column codes from right hand side to the left hand side here, from left hand side to the right hand side here, the order is going to be the same. And this row coding is the same. So what we've got here, 16 cells we've got here, for 5 variable function, you're going to have, not 16, 33 I should say, 32 cells we've got here for 5 variable functions. If you write the truth table of a 5 variable function, you're going to have 32 rows. So for each row, there is a corresponding cell. I'm not going to give you the details of an example here, but it is not easy to find the prime implicants in this 5 variable Karnaugh map. You might say in general, if you find a subcube in this, within this Karnaugh map, you're going to find this similar subcube, symmetrical similar subcube on the right hand side. Then you can say there's a subcube. For example, this 2 and this 2 make a second order subcube. And the other rules are the same. But I should explain that if you use a 6 variable Karnaugh map, then it's going to be 64 cells included. This is going to be repeated once more. Within this Karnaugh map, to find the essential prime implicants and prime implicants is not that easy. So that is the limit of Karnaugh map representation. So when it is not easy, then we are going to say that Karnaugh map method is easy to find if the number of variables are limited with 2, 3, and 4. At most 5 variable functions. After that, you cannot use the Karnaugh map method. So that limits this method. What is the benefit of this method? Since we are finding the essential prime implicants first, you can get the minimal function in very short time. So easy to find the minimal function. That's why we prefer the Karnaugh map if the number of variables in the function that we are dealing with is less. Okay, that is the comparison of the two methods as well. So I do not need to give you another video for the comparison of these
two methods. So it is explained here. Karnaugh method, speed is high, order of steps, so there's a mistake here, I will correct it. Order the step is, in Karnaugh map we find the essential prime implicant first and then the prime implicants, but in Kuhn-McCluskey method we find the prime implicant first and then the essential prime implicants. Minimum function. Another comparison is Kuhn-McCluskey method. We can find all the minimal functions, but in Karnaugh map method, it's not that easy to find to see all the minimal functions. The number of independent variables I also said. So that is the end of this video then.